The current AI industry operates on a strategy of brute force, achieving top-tier reasoning capabilities by scaling models to hundreds of billions of parameters. For enterprises, this mass introduces significant logistical hurdles. Running models of that size requires massive daily compute budgets, creates high inference latency, and forces companies to send sensitive data outside their secure networks to external cloud providers. This forces a structural question. We need to evaluate whether elite algorithmic reasoning can be mathematically isolated and extracted without relying on massive active parameter counts. These charts map active parameters against performance on math and coding benchmarks. Isolating this orange dot, ZAYA1 8B, reveals an anomaly, a sub-1 billion active parameter model that matches the scores of models equipped with 80 to 119 billion parameters. By maximizing the amount of logic extracted per parameter and per flop, we arrive at a concept known as intelligence density. This is ZAYA1 8B, a new mixture of experts language model built by the Palo Alto laboratory Zyphra. It holds 8.4 billion total parameters, but activates only 760 million during inference. From its core pre-training to its final fine-tuning, the model was trained entirely on a full stack of AMD Instinct MI300 GPUs, connected via AMD's Pollara networking fabric. The industry has operated under a preferential reliance on NVIDIA infrastructure for years. ZAYA1 8B provides evidence that the AMD stack is a viable alternative for producing top-tier reasoning models at scale. Achieving this level of intelligence density requires moving past the linear scaling mindset. The engineers executed a complete overhaul of the training stack, spanning the underlying architecture, the pre-training data mixture, and the test-time compute methodology. ZAYA1 8B shows that precise architectural specialization can bypass the hardware scaling walls currently limiting research. The foundation of this density is Zyphra's proprietary architecture, known as MoE++. On the full architecture roadmap, we can isolate 3 specific changes from standard transformer designs. The first occurs at the attention block. Standard multi-head attention mechanisms struggle with memory bloat. As prompt context grows, tracking all previous tokens eventually overwhelms the hardware. The upgrade implemented here is called compressed convolutional attention, or CCA. CCA uses a lightweight convolutional down projector to push the sequence data into a funnel. Instead of calculating the relationship between every single token in full resolution, it performs its sequence mixing inside a compressed latent space. Empirically, this produces an 8x reduction in the KV cache size compared to standard full multi-head attention. By shrinking the memory footprint of the attention mechanism, CCA frees up the computational bandwidth the model needs to perform deep reasoning and long-range recall. Moving up the stack, we reach the routing layer. In mixture of experts models, the router acts as a traffic controller, deciding which expert network handles a specific token. Standard linear routers lack expressiveness and often cause routing instability, misallocating tokens and underutilizing experts. Zyphra replaced this with the ZAYA1 router, a 3-layer MLP design featuring a technique called exponential depth averaging, which mixes the router's current data with data from previous layers. This line graph plots router entropy, or instability, against training steps. The orange line, representing the MLP router, reaches the stability threshold drastically faster than the blue linear baseline. To prevent training collapse entirely, the engineers implemented a bias balancing scheme modeled directly on PID controllers from classical mechanical control theory. Because this router is highly confident, ZAYA1-8B assigns only 1 expert per token, completely dropping the redundant residual experts required by other models. Increasing router capacity is a high leverage point. A tiny fraction of parameters perfectly commands the specialized 8 billion parameter expert pool. Moving beyond the physical architecture, we have to look at the pre-training philosophy. The standard approach in the industry treats reasoning as a post-training task. Labs typically train a base model on raw text and then try to apply reasoning logic via reinforcement learning at the end of the process. Zyphra rejected this sequence. Instead, they injected long chain of thought traces into the data mixture from step 1 of base pre-training. This creates a data engineering bottleneck. Early pre-training has a strict 4,000 token context limit, and advanced reasoning traces easily exceed that length. To bypass this memory limit, the team developed a solution called answer-preserving trimming. Mechanically, answer-preserving trimming works like a film editor dealing with a long character monologue. The system simply drops the middle of the reasoning trace. This allows the problem setup and the final answer to stitch together to fit within the 4K memory constraints. Once pre-training was complete, the model entered a 4-stage reinforcement learning cascade, which included a curriculum of 400 adaptive puzzle environments. To keep this process stable, they used router replay. The system records the exact expert choices made by the inference engine and forces the trainer to use those identical choices, preventing floating point noise from breaking the mixture of experts. Forcing the model to learn the relationship between problems and answers early, supported by stable reinforcement learning, establishes mathematical rigor as a primary structural trait. The final layer of the stack occurs at deployment, scaling the model's reasoning capabilities directly at inference. This is known as test-time compute. If you want a model to solve a harder problem, you allocate more inference compute and allow it to generate a longer, deeper chain of thought. But traditional test-time methodologies contain a critical flaw: context bloat. As the reasoning history grows into tens of thousands of tokens, standard models lose focus, the attention mechanisms degrade, and the internal logic derails. Solving this requires a shift in how we structure memory. We have to decouple thinking depth from context size. To reason indefinitely, a model must be able to process an infinite chain of thoughts without ever exceeding a strictly finite, bounded memory workspace. True intelligence scaling via test-time compute remains out of reach until context size and thinking depth are decoupled. ZAYA1 8B solves context bloat natively using a methodology called Markovian recursive self-aggregation, or RSA. In step 1, a single prompt causes the model to generate multiple parallel reasoning traces simultaneously. In step 2, the system drops the majority of those traces. It extracts only the tails, the final few thousand tokens of each candidate. Finally, these extracted tails are subsampled and fed back into the model inside a new aggregation prompt. The model is asked to review the tails, reconcile the different approaches, and output one superior solution. Looking at this AME 25 benchmark chart, the results are startling. By continuously carrying forward just a 4K token budget, Markovian RSA pushes ZAYA1 8B to a 91.9% score. This recursive boost closes the gap, competing directly with massive frontier models like DeepSeek v3.2 and GPT-5 High. For enterprises, this changes the deployment reality. Because ZAYA1 8B is released free under an Apache 2.0 license, companies can run high-tier, local-first reasoning directly at the edge, eliminating the need for expensive APIs or massive cloud dependencies. ZAYA1 8B provides evidence for the efficacy of recursive algorithms, smart data curation, and dense routing, achieving peak intelligence density without relying on brute force parameter classes.